For over a century, we've believed that space and time are the fabric of reality. Einstein showed us that they're woven together into spacetime, a four-dimensional structure that bends, warps, and curves. But cutting-edge physics is revealing something shocking. Spacetime might not be fundamental. It might be an illusion, an emergent phenomenon that appears at large scales but breaks down at the smallest. Just as temperature emerges from the motion of atoms, but isn't a property of individual atoms, spacetime might emerge from something deeper, something quantum, something we don't yet fully understand. Welcome to the quantum gravity revolution, where the most basic features of reality, space, time, distance, duration, are being questioned. And physicists are starting to believe spacetime is doomed. Einstein's general relativity is one of the most successful theories in physics. It describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Stars, planets, even light. Everything moves along curved paths dictated by the shape of spacetime around them. The theory has passed every test. We've measured gravitational time dilation. We've detected gravitational waves from colliding black holes. We've photographed event horizons. General relativity works, but it's incomplete, because it can't be reconciled with quantum mechanics. Quantum mechanics governs the behavior of particles at the smallest scales. It's probabilistic, discrete, and deeply weird. Particles exist in superpositions, entangled across vast distances, and their behavior only becomes definite when measured. Quantum field theory, the framework that combines quantum mechanics with special relativity, is also stunningly successful. It describes electromagnetism, the strong and weak nuclear forces, and has made predictions accurate to 15 decimal places. But quantum mechanics treats spacetime as a fixed background. It assumes space and time exist independently, providing a stage on which particles perform. General relativity says the opposite. Spacetime is dynamic, shaped by matter and energy. These two pillars of modern physics are incompatible at a fundamental level. The conflict becomes undeniable in extreme conditions, inside black holes, at the Big Bang, or at the Planck scale, about 10⁻³ meters and 10⁻43 seconds. At these scales, quantum effects and gravitational effects are both strong. You can't ignore either. But when you try to apply both theories together, you get nonsense, infinities, singularities, mathematical breakdowns. General relativity predicts smooth, continuous spacetime. Quantum mechanics predicts a roiling foam of fluctuations. Something has to give. For decades, physicists have sought a theory of quantum gravity, a framework that unifies the two, and in the process, they've begun to suspect that spacetime itself is not fundamental. One of the leading candidates is string theory. In string theory, particles aren't point-like objects, they're tiny vibrating strings. Different vibration modes correspond to different particles: electrons, photons, quarks. Crucially, one vibration mode corresponds to the graviton, the hypothetical quantum particle that mediates gravity. String theory requires extra dimensions, 10 or 11 total, depending on the version. Most of these dimensions are compactified, curled up so small we can't detect them. But the theory naturally includes gravity as a quantum phenomenon. Spacetime, in string theory, emerges from the interactions of strings. It's not the starting point, it's a consequence. At very high energies or small scales, the usual notions of space and time dissolve. What remains are strings vibrating in a pre-geometric background. String theory also led to a profound idea: the holographic principle. This emerged from studying black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of information. Surprisingly, this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. That suggests all the information inside a black hole is somehow encoded on its surface, like a hologram. Physicist Leonard Susskind and Gerard 't Hooft generalized this. Maybe all the information in any volume of space is encoded on its boundary. A 3D region might be fully described by 2D data on its surface. If true, our three-dimensional experience of space might be a projection, an emergent description of something fundamentally two-dimensional. The ADS-CFT correspondence, discovered by Juan Maldacena in 1997, made this concrete. It's a mathematical duality between a gravitational theory in a higher dimensional curved space, anti-de Sitter space, and a quantum field theory without gravity in one fewer dimension, a conformal field theory. In simple terms, a universe with gravity can be exactly equivalent to a universe without gravity, just with one less spatial dimension. Space-time with gravity is an emergent, holographic projection of a lower-dimensional quantum system. This was a bombshell. It implies that space, time, and gravity are not fundamental. They're derived properties of something more basic. Another approach is loop quantum gravity. Unlike string theory, loop quantum gravity doesn't add extra dimensions or require strings. It quantizes space-time itself. In this picture, space is not continuous, but made of discrete loops, tiny quantum threads woven into a fabric called a spin network. These loops are incredibly small, at the Planck scale. At large scales, the spin network looks smooth, like how a fabric looks continuous from a distance, but is made of threads up close. Time also becomes discrete, ticking in Planck time intervals. There is no before the Big Bang in loop quantum gravity because time itself is emergent. At the Big Bang, space-time condenses from a quantum state where classical notions of before and after don't apply. In this view, space-time is not the stage, it's an actor, and at small enough scales, the actor dissolves into quantum geometry. Both string theory and loop quantum gravity suggest space-time is emergent. But emergent from what? Some physicists propose information. John Wheeler famously said, "it from bit," the idea that physical reality arises from information. In quantum mechanics, information is fundamental. Entanglement, superposition, measurement, all are informational concepts. Maybe space-time is just a convenient way of organizing quantum information. When quantum systems become highly entangled in certain patterns, space-time geometry emerges. The distance between 2 points isn't a fundamental property. It's a measure of how entangled the quantum states at those points are. The more entangled, the closer they are. This idea, called entanglement entropy, is being actively researched, and preliminary results are promising. In some toy models, space-time curvature corresponds exactly to the structure of quantum entanglement. If space and time are emergent, what does that mean for causality? In classical physics, cause precedes effect because time flows in one direction. But if time is emergent, causality becomes more subtle. Maybe causality is also emergent, a macroscopic approximation that breaks down at the quantum level. Some theories, like causal set theory, propose that the fundamental structure of reality is a network of causal relationships. Space-time is what you get when you smooth over this network. Events are nodes. Causal connections are edges. Distance and duration emerge from counting steps in the network. This is radically different from thinking of space-time as a container. It's more like a web of events, with no background at all. Physicist Nima Arkani Hamed has gone even further. He suggests that space-time is not just emergent, but doomed. In his research on the amplitude AI geometric structure that simplifies particle physics calculations, space-time doesn't appear at all. Predictions about particle collisions can be computed directly from abstract geometric shapes in a higher dimensional space, without ever referencing positions in space or moments in time. The answers match standard quantum field theory perfectly, but the calculation bypasses spacetime entirely. If spacetime is unnecessary for the math, maybe it's unnecessary for reality. Maybe it's just a useful fiction, like epicycles in pre-Copernican astronomy, a model that works but isn't true. This has philosophical implications. If spacetime is emergent, then the universe doesn't exist in space or evolve in time. Those concepts only make sense at our macroscopic scale. At the fundamental level, reality might be timeless and spaceless, a vast web of quantum correlations or abstract mathematical structures. Our experience of being located in space and moving through time is a kind of cognitive illusion, a high-level approximation our brains use to navigate a quantum reality that doesn't inherently have those features. Kant argued that space and time are not properties of the world, but forms of human intuition, ways our minds structure experience. Modern physics is starting to agree, but for very different reasons. What would a world without fundamental spacetime look like? We don't know. We've never experienced anything else. Every experiment we do takes place in space and time. Every thought you have unfolds temporally. Every object you see exists spatially. Even trying to imagine non-spatial, non-temporal existence is nearly impossible. But mathematics doesn't care about imagination. If the equations work without spacetime, then spacetime might be optional. Reality at the deepest level could be something utterly alien, a Hilbert space of quantum states, a spin network, a holographic boundary, a causal graph, structures that don't look or feel like the world we inhabit, but from which our familiar world emerges. Testing these ideas is extraordinarily difficult. Quantum gravity effects are expected to become significant only at the Planck scale, distances 20 orders of magnitude smaller than an atomic nucleus. No conceivable particle accelerator can reach those energies. We can't build microscopes that peer into the quantum foam, but there are indirect approaches. Gravitational wave detectors might spot subtle quantum signatures in space-time ripples. Cosmic rays from the early universe might carry imprints of quantum geometry. Black hole thermodynamics offers theoretical constraints, and advances in quantum computing and condensed matter physics are creating laboratory systems that mimic aspects of quantum spacetime, allowing physicists to test ideas in miniature. One tantalizing clue comes from black hole information paradox solutions. Recent breakthroughs using holography and quantum error correction suggest that information is preserved in black hole evaporation, but only if spacetime near the horizon behaves in non-classical ways, entangled, non-local, holographic. These solutions require that spacetime connectivity is not fundamental, but arises from entanglement. Two distant regions of space are only far apart because they're not entangled. If you entangle them strongly, they become connected. You create a wormhole. This is the ER-EPR conjecture. Einstein-Rosen bridges, wormholes, are equivalent to Einstein-Podolsky-Rosen pairs, entangled particles. Spacetime geometry and quantum entanglement are two sides of the same coin. Space is not a container. It's a pattern of quantum correlation. If all this is true, then the universe's history needs rethinking. The Big Bang wasn't an event in space and time, it was the emergence of space and time. Before, if before even means anything, there was only a quantum state. As that state evolved, spacetime condensed out, like ice forming from water. The smooth spacetime we see today is a low-energy approximation. At high energies, near the Big Bang, inside black holes, spacetime dissolves back into its quantum substrate. The universe didn't start with space exploding. It started with quantum information crystallizing into geometry. This also affects cosmology. If spacetime is emergent, Then questions like, what came before the Big Bang, or what's outside the universe, might be ill-posed. They assume space and time extend beyond the observable universe. But if space-time only exists where quantum correlations create it, then the universe doesn't have an outside or a before in the usual sense. The boundaries of space-time are not walls. They're the edges of the region where space-time is a good description. Beyond that, there is no beyond, not emptiness, not void, just the failure of space-time as a concept. Some physicists find this liberating. It means the universe doesn't need a cause in the traditional sense. Causation requires time. If time is emergent, then asking what caused the universe is like asking what's north of the North Pole. The question doesn't apply. The universe simply is, in a timeless, quantum sense. From within the universe, we experience time flowing, causes and effects unfolding. But from a God's eye view, if such a view existed, there is no flow, just a static quantum state, and we are patterns within it, experiencing the illusion of time. Others find it unsettling. If space and time aren't real, what is? Are we real? This is where physics meets existentialism. But the answer is subtle. Emergent doesn't mean fake. Temperature is emergent. It arises from molecular motion, but it's still real. You can burn your hand. Similarly, space-time is emergent, but it's real at our scale. The table in front of you is solid, even though it's mostly empty space filled with quantum fields. The solidity is emergent, but you still can't walk through it. Space-time is the same. It's emergent, but it governs your life completely. The deeper quantum reality matters for black holes and the Big Bang. For you, in your kitchen, space-time works just fine. Yet the implications ripple outward. If space-time is doomed, then so are many cherished ideas. The notion that the universe is a vast arena where events play out. The idea that time is an objective flow. The assumption that causality is fundamental. All these might be provisional truths, useful at our scale, but not ultimate. Physics is moving toward a picture where reality is relational, informational, and quantum, where the universe is not made of stuff in space-time, but of correlations and entanglements from which space-time emerges. It's a shift as profound as the move from Newtonian absolute space to Einsteinian curved space-time, and we're living through it. So what comes next? We need experiments, we need mathematical breakthroughs, and we need new ways of thinking. Because space-time is so deeply embedded in how we think, language, intuition, perception, that imagining physics without it is almost impossible. But that's what's required. Future physicists will have to think in terms of quantum information, entanglement networks, and abstract geometric structures. They'll have to build intuition for worlds without space or time. And if they succeed, they'll understand reality in a way we can barely glimpse. They'll see the universe not as we see it, objects in space, events in time, but as it truly is, a pattern of quantum information weaving itself into the illusion we call space-time. And in that moment, physics will have transcended space-time entirely. The stage will have dissolved. Only the play will remain.